final talk today will be by Alfredo Deaño. He's going to talk on Painlevé equations and non-Hermitian random matrix ensemble.
Thank you very much, Peter. Thank you very much to the organizers for the invitation. It's really great to be back in Cambridge. So, since this is the last talk of the day, and also I'm between you and a wine reception, then I'll try. I'm going to make this as easy and as general as possible, and then of course any questions I'll be happy to elaborate if anyone is interested. So this is so part of it. So the first part will be more of an introduction. The second part is joint ongoing work with Nick Simm. Some of you know him well. He's currently at the University of Sussex, and he works on random matrix theory. So what we are interested in, that will be, I'll come a bit later, is the, and I'll explain what all these concepts are, the study of the partition function and characteristic polynomials in random matrix ensembles. And more precisely in non-Hermitian random matrix models, and then this is where the complex analysis, the complex variables will come in. And we are interested in also in identifying these quantities related to this analysis, this partition function, this expectation of characteristic polynomial, in terms of solutions of Painlevé equations, both for finite n as n tends to infinity. So I'll briefly say a bit about Painlevé equations. I hope it's not too much of a spoiler for Peter's talk tomorrow and next days. And the other aspect that I find interesting is, well, the method that we are going to use for this analysis is the method of orthogonal polynomials. So this is very well known in the case of Hermitian random matrix ensembles. This is what I'm going to describe first. And then basically the idea is, okay, how far can you push this into the complex case? And some things work fine, and some other things not so fine, but it's also interesting to see the limitations of the method. And a little bit of this game of the formation equations in parameters that we've heard before in the talk of Jonathan. So that will appear here briefly. So as I said, Hermitian random matrix ensembles, this for the experts is probably very well known, as well as the method of orthogonal polynomials. But as I said, my goal is to describe this method in a slightly different context. Painlevé equations, briefly, because we'll get quite a bit of it later in this week. And then the non-Hermitian ensembles that we are considering are, well, complex Geneva ensemble and truncated unitary matrices. I'll describe that. And then, well, some of the results that we have for finite n and the one for large n are kind of halfway. Okay, so in random matrix theory, okay, this is a huge area of research that brings together people from many different areas of mathematics and also physics and statistics, which is good, but sometimes it's a bit can be a bit confusing. Too many references and too many ways of approaching similar ideas. One point of view that is probably the most immediate to random matrices is the one coming from probability. So you have a matrix where the entries are random variables with a certain distribution. Maybe the matrix has some structure, maybe it doesn't. And then you try to, well, say things about this random matrix, and typically you would need probability theory, measure theory, and that kind of machinery. The other point of view, or another point of view, is you have a set of matrices with some structure, okay, and then you add a probability law, a probability measure on it. That's where the randomness comes in. So in this case, the structure is very much fixed, and that makes the analysis quite different. There are a few examples where these 2 points of view kind of coincide, but in general, the tools that you use here are more of integrable systems, math physics, if you want to call it, rather than probability theory. So if you go and you look for the literature on random matrices, then typically you will find, well, it's very different depending on your approach. Just a warning. So in this second point of view, which is the typical one if you enter random matrix theory from the area of special functions or math physics, that sounds a bit more fancy, is the following. So suppose that you have, well, start with Hermitian matrices. This is the simplest case. Capital N by capital N, this is always going to be the size of the matrix. And then the probability measure has a, well, form that is maybe a bit strange if you haven't seen it before. This is a normalizing constant or partition function, if you follow the physics vocabulary. Then you have this term. This is an exponential term, minus n. This is just scaling. And then you have trace of some function of your matrix. So because it's the last talk, let's keep v as a, well, think of an analytic function with sufficient growth at infinity. Even a polynomial, if you prefer, that will be fine. So polynomial with positive leading coefficient, that's fine. The only requirement basically is that you can normalize this thing on the real line, so that you have enough decay. And dm is Lebesgue measure on the entries of n, which is a bit of a strange object. One very important property here is that this measure is unitarily invariant. So if you take your matrix, you conjugate by unitary, then you essentially get the same probability law. This requirement typically is explained by saying that, okay, in the origins of this approach to random matrices comes essentially from physics. And then this kind, this kind of invariance essentially says that your matrix, if you think that it's describing a very large statistical system, then you want whatever you are observing, whatever you are describing, to be independent of changes of variable, rotations, translations, that kind of thing. So that's a bit like the idea of where this unitarily invariant property comes from. And this really is imposing a lot of structure in the system. Okay. So this is the general setting. And then, well, people have looked for already quite a few years at quantities, well, ideally for finite n as well, but for finite n, if n is very large, then things become quite complicated. In the asymptotic limit, as n tends to infinity, then you can hope to get some kind of global information or local information that is somehow independent of small details of how your random matrix ensemble is constructed. This is the whole universality idea. So for example, if you look at the eigenvalues of your matrix, you have a Hermitian matrix, the natural quantities, eigenvalues, eigenvectors. You may look for global information. And what I mean by that, for example, you take the counting measure of your eigenvalues normalized by n. This is a discrete probability measure, and you say, okay, what happens if I let n tend to infinity? Do I have a limit in some sense? And the answer is, well, in many cases, the answer is yes. You get a convergence, at least in weak sense, convergence of measures. And the typical example that I'll show in a minute is Wigner's semicircle law. That's the prime example of global behavior of eigenvalues in Hermitian random matrices. But you can also look at local statistics of eigenvalues. And this has appeared before. Correlation between eigenvalues, gap probabilities appeared today. Distribution of the largest eigenvalue, the smallest eigenvalue, and so on. And there, one of the things that people want to show is universality in the sense that if you change your potential V in some sense, okay, what properties stay roughly the same? Okay. The global picture is probably not going to be the same, but maybe the distribution of the smallest eigenvalue, if instead of a potential like this, you have a potential like that, then it's same kind of result. And another thing that you can wonder is, okay, what happens with the partition function and this related quantity, which is the free energy? So you let n tend to infinity. Typically, there will be parameters in this partition function. And then what happens as n tends to infinity? What you get, is it uniform in parameters and so on? So this is the main example in Hermitian random matrices. The first case that you normally encounter is the GUE, the Gaussian unitary ensemble, where your potential is just a quadratic. And in this case, actually, you can approach GUE from the point of view of, okay, this is the potential and this is my probability measure on Hermitian matrices. But you can also you can sample GUE by taking random variables and put them in a matrix. So if you take capital N by capital N matrix Y with independent random variables with normal distribution, and then you take 1/2 of Y, Y star, then you get a Hermitian random matrix, and this belongs to GUE. So very easy to sample. And then, okay, this is classical theory. This is the global picture, for example. Here's a histogram of eigenvalues for different values of n. And this red curve is which is the semicircle law, Wigner's semicircle law, which is the limit density on -2,2 with this normalization. Okay. So of course, this doesn't prove that there is convergence to this in any sense, but okay, there is. And then, well, this is the global density of eigenvalues for GUE. This is another picture that I think is interesting because it's more of a local behavior, if you want. So the first and the third, the points in the black points are just random or pseudo-random numbers in MATLAB taken in the interval -2,2. And the blue ones, the second and the fourth, are eigenvalues of a GUE matrix of the same size, so the same number of points. Now the picture is not a proof of anything, but qualitatively these configurations are typically very different. So if you have pseudo-random points, you get typically big gaps here and also clusters or almost clusters of points. Whereas in the case of GUE, you get, well, not a uniform distribution, but the eigenvalues, the points are much more evenly spaced. Okay.
So those pictures suggest that you can't have eigenvalues outside the interval, but of course you can. Right?
You can, yeah. That could happen, yeah, definitely. This is a soft edge, so the probability is very low, but you could have eigenvalues, yeah. In GUE, yeah, if you take a Laguerre, for example, then you have positive definite, then the origin is a hard edge. That's a different case, yeah. So what you normally do in order to, well, what you can do to analyze this Hermitian random matrix ensembles, the first thing that you do is you go for the spectral decomposition of your matrix because you want to write the probability density function in terms of eigenvalues and eigenvectors, much better than on the entries of the matrix. So you get, okay, a new partition function here, and here's it's a simpler case of what Jonathan was showing before. This is a probability density function on the eigenvalues. It would be the case theta equals to 1, actually, simplest one. And then, well, if you arrive here, then if you want, you can forget about random matrix theory and then just study random configuration of points on the line following this distribution. Okay, and that's okay. These two terms, actually, the first one is a repulsion between eigenvalues, as was said before. If you have points, configuration with points very close together, then that probability is going to be very small. So the eigenvalues repel each other in a way. This is this term, this van der Monde determinant square. And then you have a confinement that prevents eigenvalues from flying to infinity. And this confinement basically depends on the potential V. It grows at infinity, so it's pushing eigenvalues away from infinity. And then, okay, you have these two phenomena, and then this is the point of view of interacting particle systems. You have this very particular interaction, and you wonder if there is for example, if there is a limit configuration, non-trivial limit configuration. And this typically happens when these two effects operate at the same scale. So you scale the variable or the parameters in such a way that the confinement and the repulsion are comparable. Okay, so that's one point of view where random matrices leads you to interacting particle systems. But from here, you can also continue, and then you manipulate this determinant a little bit, and then you write it in terms as a determinant with a correlation kernel, Kn, this function of two variables. Okay, this is a new partition function here. It's just accumulating all the constants that you have with all these manipulations. And then this kernel, easy to convince yourself, is kind of half of this on the other side, and then the product of the two Vandermondes. And in general, you can have any polynomial here, because you take the Vandermonde, it doesn't have to be a monomial. You can do row and column operations, and you have the polynomials that you want, degree k and degree k, just multiplication. So this formula, this representation is very nice. It shows that this is a determinantal point process, which is another area, big area of research. But it's not very clear how it helps for large n asymptotics, because you write this, okay, you have your kn, but this sum, if I let n tend to infinity, it becomes very difficult to control. The point here is that precisely because you have this freedom in choosing these polynomials qk, if you choose, and here's where the orthogonal polynomials come in, if you choose an orthogonal basis, so orthogonal polynomials with respect to this weight function is an exponential weight on the real line, and orthogonal in this L2 sense. So product of the two polynomials with respect to the weight equals 0 if the degree is different, and positive constant if the degree is the same. Then this orthogonal polynomial satisfy a three-term recurrence relation, is one of the important properties. So there's a relation between Qn plus 1, Qn minus 1. And then this allows you to telescope this kernel. This is the Christoffel-Darboux formula. And then you end up basically with two polynomials instead of the whole sum. So really, that is a big improvement. If you want to do asymptotics, then you just have to control polynomial of large, orthogonal polynomials of large degree, which is a well-known problem in the theory of orthogonal polynomials. Okay. So that's essentially how it works. The method, okay, has a lot of computations, but essentially the point is that if you can control this kernel, then you have access to basically all the information that you need about your random matrices. For example, correlation functions or marginal distributions on eigenvalues. And this is a nested integral where you integrate out some of the eigenvalues. In particular, if you are left with 1, then you basically get the density of eigenvalues. Then you have a two-point correlation function and so on. This is quite unpleasant to work with. There's a multiple integral. But in terms of the correlation kernel, this is just a determinant of size, well, whatever correlation function you want to compute. So not too bad. If you control k, well, you still have a determinant, but okay, things look much better than with this integral. And also, this appeared before, the gap probability, so probability that the matrix has no eigenvalues on a certain interval. This gap probability can be written as a Fredholm determinant. And what you have here is the operator with kernel, this kernel acting on L2. So this kernel could be kernel of orthogonal polynomials, could be a sign kernel, could be the Airy kernel, whatever. Okay. Right. So everything, in a way, boils down to this correlation kernel. What do you do for the partition function? Well, I'm not going to go into the details that we saw before, but essentially it's the same idea. For the partition function, you try to write, well, you have a formula in terms of orthogonal polynomial quantities. This is the product of the norming constants. This is not very nice formula, but these norming constants are not very explicit unless you have one of the classical families of orthogonal polynomials. This is, well, this is this integral. With n equals to m, well, difficult to compute in general. Okay, you don't like the product, you take the logarithm, and then you convert it into a sum. And then you try to manipulate this sum, but this is not as nice as the previous one, where you could use Christoffel-Darboux. So the typical one of the games that people are playing is, well, the formation with respect to parameters. We saw that before. If you have a parameter in your partition function, or even if you don't, you can introduce a parameter, and that's a bit of the, I mean, it depends where the parameter is. This can be more or less complicated. If you have a parameter t, then you try to write a differential equation for log derivative. And then when you differentiate, these things become more tractable in terms of recurrence coefficients for the orthogonal polynomials and so on. Then if you get a decent differential equation, one that you can manipulate, then you go for asymptotics of whatever you have on the right-hand side. You replace and you integrate in parameter space. So as we saw before, this can be very, very complicated depending where your parameter sits. If your parameter is in the potential e to the minus n v whatever, then things are not too bad. If your parameter is an exponent of an algebraic term, then your life can get exciting. But this is the recipe in principle, and then it's a bit of a, well, this is skill to see if you can put a parameter somehow deform and get a good differential equation. But even if you do, then there are a couple of issues that depends how rigorous you want to be, can become a problem. The first one is the initial value where you integrate from. Otherwise, you're stuck with the problem of computing the constant. As we saw before, that can be, well, if you're happy with unknown constants, fine. If you want the constant, then this is important, where you start. And sometimes, well, your initial value might be at infinity, for example, and then you need some kind of uniformity. Or maybe you want to integrate over different asymptotic regimes. So you have an asymptotic expansion for this, for whatever quantities in the differential equation, but then maybe these asymptotics are not uniform. So then you have to make sure that all the regimes overlap, and that can be quite technical. Okay, but again, it's the method of orthogonal polynomials, just one step further. So in the end, if you have large n asymptotics of orthogonal polynomials, then in principle you are in business to understand this kind of ensembles. And for this, you can have, okay, integral representations, differential equations, recurrence relations, and, well, if not, then you can go for the heavy artillery of Riemann-Hilbert and nonlinear steepest descent, which in this case, I mean, if you have this kind of weights, e to the minus nv on the real line, is not too difficult. I mean, it's quite technical, but things should work. Now, the point is that in these asymptotics, normally you will need classical special functions. For example, if you're trying to describe the orthogonal polynomials in the interval where they have the zeros, then the asymptotics will typically be trigonometric. Outside could be exponentially decaying. In between, you may need an Airy function to handle this transition, or a Bessel function, hypergeometric if you really go for more complicated cases. But if this is not enough, then, well, there are cases where you have to go to Painlevé. And very briefly, so Painlevé functions, or nonlinear special functions, so Peter will probably describe much more tomorrow and the next days. So are solutions of the 6 Painlevé differential equations, typically labeled P1 to P6. I didn't write the 6 of them, but you can find them in the DLMF, for example. So essentially, these equations appear in the problem of classification of second-order nonlinear differential equations with extra properties that make the problem tractable in a way. So this right-hand side is rational in U and U prime, and you also impose that any solution, this is the Painlevé property, any solution is free of movable branch points. So you have a nonlinear differential equation, the solution can be as crazy as you want, but you don't want any branching points, any logarithm singularity or algebraic singularity depending on initial or boundary conditions. Movable poles is fine, fixed algebraic singularities is fine, for example. So these are two, number 2 and number 4, Painlevé 2 and Painlevé 4 in the list of in the standard list of 6 differential equations. And okay, from this functions appear in the problem of classification of ODEs. And in general, the solutions, I mean, this was filtered in such a way that, well, the solutions of these differential equations are not reducible in general to classical special functions or elementary functions. So that's why sometimes they are called nonlinear special functions. They are really transcendental in that sense. However, it's important to know that for some values of the parameters, P2 to P6 have solutions that reduce to elementary or classical special functions. And these ones appear in random matrix theory. Sometimes it's a full transcendental solution, sometimes it's one of this, and I think it's important to make the distinction. Some applications of Painlevé. Well, the list goes on and on. From combinatorics, this was a very nice paper of Pike, Tate, and Johansson 20 years ago in an apparently completely different problem, the length of the longest increasing subsequence in a random permutation. They appear in integrable systems when you do reduction of some integrable PDEs. Statistical physics, Ising model and other models in statistical mechanics. This was essentially what the revival of Painlevé functions in the 60s. Relation with orthogonal polynomials, typically parameter deformation of classical families. There are many examples. I should have quoted the book by Walter, the recent one, where he discusses many examples of orthogonal polynomials and Painlevé equations. And in random matrix theory, they appear, well, basically all over the place, in different, but in quite different contexts. So where do we need these nonlinear special functions? Well, here's one example. When you look at extreme eigenvalues, so if you take GUE that we saw before, and then you look at the largest eigenvalue. The largest eigenvalue scales, this is standard scales like a square root of 2n. N is the size of the matrix. And then you look at fluctuations around this value of very precise scale. And then this has a limit, call this function f2 of s. Then the big famous result of Tracy and Widom in the 90s is that this f2 can be written as an exponential of minus integral, and what appears here is actually a solution of one of the Painlevé equations. It's Painlevé 2 with this parameter alpha equal to 0 and very precise asymptotics at infinity. And this is the Hastings-MacLeod solution. So this was one of the big results connecting solutions of Painlevé equations with random matrix theory. So this is one example. The second one is when you have some sort of critical transition. So you may have an ensemble. This is, for example, with this potential, that you have a parameter t. And then there is a transition at the critical value, explicit critical value. And then if you look at the limit, the global density of eigenvalues, then the support goes from one interval to two disjoint intervals. And then near this transition, then what you need in order to describe this correlation kernel, for example, is again Painlevé functions, solutions of Painlevé 2. Okay? And there are other types of transitions where you need Painlevé. For example, if one of the behavior at one of the endpoints of the support changes, for example, or things like that. Okay? This is a kind of critical transition in the behavior. Because then the asymptotics here and here, the asymptotics of the orthogonal polynomials are essentially different. So if you want to glue them, then you need this analysis near this transition point. And this cannot be covered with classical special functions. Okay? And the last example is gap probabilities. This is for finite n. So before it was as n tends to infinity, and the solutions, I forgot to mention, the solutions that you get here and here, these are transcendental, fully transcendental solutions of P2. If you look at finite n, same GUE, and then you ask, okay, what is the probability that no eigenvalues on S in S infinity? Okay, now again, Tracy and Widom, this is exponential of minus integral, but then what appears here is not a solution of P2 is a solution of P4. Actually, the sigma form, which is a related differential equation, connected with Painlevé 4. Okay? And important detail here, actually, this is a special function solution for finite n. So this one is a solution of Painlevé 4, but you can actually write it in terms of classical special functions. Kind of simplifies it a little bit. Okay. So these are the three connections that I wanted to point out. And now, non-Hermitian case. So the point is to see, okay, how much of this carries through to a non-Hermitian ensemble. So the way we study it is we consider the set of n by n. Now Hermitian goes away, just matrices. But I keep a probability law with the same form. Okay, partition function. Van der Monde, now I put a modulus because everything goes complex. The eigenvalues are going to be complex. And then, well, I have some weight here, maybe an exponential kind of thing, or maybe something different. And now, okay, and then I have to take an area measure in the complex plane. So it's kind of analog, copy and paste, of the Hermitian case. Zn is a partition function, and still have the unitary, the invariance and the unitary conjugation. So I'm basically copying the structure of the probability law and see what happens. Examples. Well, this is the evil twin, or you want the non-Hermitian twin of GUE. This is the complex Ginevra. Exponential, and I just add modulus. What could go wrong? So this was studied by Ginevra in the 60s, and this complex Ginevra, this is not too bad. The real Ginevra ensemble is much harder. But okay, stay with complex. The normal matrix model, where you consider instead of Hermitian matrices, normal matrices. This is a good source of examples here. You can add to the Ginevra, you add some potential here, and then, well, depends what you add. You have to be careful because if you want to normalize this in the whole complex plane, then this should dominate over V and V bar. Otherwise, you have to take cutoff functions or regularizing it in some way. There are quite a few papers in the literature about this with different potentials. Okay. Another example. Well, these kind of weights are quite nice to work with. So you consider exponential, then you have a dominant power here, and then you put some lower order terms. This was studied quite recently. And okay, one of the questions that we'll see in a minute is what is the support of the equilibrium measure? Everything goes to the complex plane, so where do the eigenvalues go? And then this other kind of particular case here, where you have power 2D, power D and D, this it's called the lemniscate ensemble. It will be clear in a minute. And then this even more recent paper, the Balogh, Grab, and Merzi, looked at the limit zero distribution asymptotics for orthogonal polynomials. So there are orthogonal polynomials here, but they are going to be in the complex plane. Okay, so I have this non-Hermitian ensemble with whatever, well, this could be W. I put an exponential weight here, but it could be a different thing if you want. Question, what is the global behavior of eigenvalues as n tends to infinity? So what is the global picture? And the answer, well, if V decays rapidly enough at infinity, and you scale things properly, then the eigenvalues, complex, will be confined in a compact region, which is sometimes called the droplet. But now, instead of being one interval, like in the semicircle law, then it's going to be something in the complex plane. Okay. This is no very precise answer, but okay. First example, Ginevra. So you take the potential. This is quadratic. The partition function is very explicit. And then again, you can do this. You can sample this easily. Just take a random n by n matrix, now without making the Hermitian variant, but build out of standard Gaussian entries. And then you compute the eigenvalues. This is the normalization that you should use, 1 over square root of n. So the eigenvalues are confined on the unit disk. So this is the droplet in Ginevra. This is very simple. And again, this is a soft edge, so there can be eigenvalues outside, but with low probability. And eventually, this is a theorem, they will fill the unit disk with uniform area measure. Okay, so this is the result for Ginevra, which is, if you want, a 2D analog of the semicircle law. Okay. Right. This is another example. Suppose that you have an M by capital M unitary matrix, taking from this would mean just another set of random matrices, the circular unitary ensemble. And then you take an n by n minor. You can take the n by n upper left corner, the principal minor. Then, if you are interested in the probability density function for the eigenvalues of this truncation, of this block, then this is known, has exactly this structure, and then the weight here is not the exponential minus n blah 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 like in Ginevra, but it's an algebraic thing. And now you have these two parameters m and n, and this is supported on the unit disk. So if you want to do asymptotics here, then now you have two parameters to play with, and basically you can have two different situations. Ginevra type, where both parameters go to infinity, but you keep n over m fixed. Okay. Then you are basically, in Ginevra case, more or less, then the droplet is a disk of radius square root of this limit parameter. Okay, it's a disk, but smaller. If you do not truncate too much, then you are in the weak non-unitary regime. So both go to infinity, and you basically chop off just a finite number of rows and columns, and then the eigenvalues cluster near the unit circle. So you're basically almost unitary. Okay, there's a distribution on the unit disk, but they basically cluster near the unit disk. So this is the first case. So this would be a disk. It looks like a unit disk, but it's not. The radius would be the square root, more or less the square root of 0.1. No, it's not. It's 0.1 over 1 plus 0.1. Okay, whatever number. And this is another case. And the density is actually not uniform density. So the eigenvalues, the density is higher as you approach the boundary. Okay, but there will be eigenvalues inside. Okay, they don't go to the unit circle. If you are in the weak non-unitary regime, then well, basically you have almost unitary matrices. They just have, because you are truncating, then you still have some people here inside the unit disk. Okay. Right. So these are the two examples. Two main examples that we consider. And then the question is, well, we want to understand the partition function of this kind of ensembles. And more in general, you can ask what is the behavior of the characteristic polynomial. So in the characteristic polynomial, you compute the expectation of this object. And this you can think of as adding charges or points, zi and wi bar. So you add 2 k points to your ensemble. And then you may wonder, okay, how this behaves, for example, as n tends to infinity. What is the effect of adding these charges? These ensembles that I mentioned before have a very interesting advantage. They are rotational invariant, and that makes calculation much simpler. So in complex Ginevra, it's just this exponential. Truncated unitary is this algebraic, but in both cases, this is rotationally invariant, and then the calculations that will follow are much simpler. Okay. So this is the lemniscate ensemble that I mentioned before. So this is the partition function. Your potential is power 2D and then two lower order terms. And then this is the limiting eigenvalue distribution. So you have a critical value Tc, very explicit, the square root of d, where d is this parameter. So in this case, the square root of 11, I think it was. Before this critical value, you have a connected set as limit eigenvalue distribution. There will be the support will be this connected set. Then you go through transition at the critical case, and then the support becomes disconnected.
Presumably at the center of the center figure.
Yeah.
That's not correct.
No, there is a point there. Yeah. There is a point. Yeah, thank you. That was MATLAB then.
What sort of computation led to that coming out wrong? I don't get it.
I don't know, but it was very explicit because it's just plotting a lemniscate and then rotating. So it's probably mine. Yeah. Yeah, that's definitely a point. Yeah, there's no gap in there. Yeah.
That person should take a course from a numeric analyst.
Yeah. Okay, so essentially what is happening here is not a surprise. The partition function in this case is just a multiple of, a product, of partition functions of Ginevra. Okay, because you're basically, if you make the change of variables z to power d equals u here, then you basically fold it. And then what you get is a product over all the way to d of these Ginevra partition functions. But okay, the price for this change of variables is that you get this kind of algebraic term here. So it's Ginevra times this. And then you can see, okay, this was a calculation coming from a rotational symmetry of the model. Now you can look at this as expectation of a polynomial with respect to this ensemble. Just by definition, expected value of product of zj minus x to power gamma l. Okay. So this is one way. Whenever you have a rotational symmetry, you will typically end up with whatever weight you have times this kind of factor. So how do you study this? Well, if you copy what worked in the case of Hermitian ensembles, then you want to use orthogonal polynomials. This is fine. Now you need orthogonal polynomials in this complex sense. If you want true orthogonal polynomials, then you need this complex conjugate here. So it's an inner product. But the problem here, okay, there's nothing wrong with this kind of orthogonality. The problem is that when you try to simplify the correlation kernel, then, well, things go a bit wrong here because you don't have the nice recurrence relation that allows you to simplify this sum. So you're basically stuck there. Okay, so that's not very nice, but there are ways around it. So a couple of solutions. The first one is a formula that by Ackermann and Vernizzi in the random matrix theory literature that gives some sort of duality. I will explain what that means in a moment. This allows you to work with the correlation kernel without trying to simplify it right now, and it gives nice results. The only thing is that it's limited in the parameters that you can use. This gamma L that appear here will not, it will have to be an integer, okay, which is a limitation. The other thing that you can do is reduce this complex, planar orthogonal polynomials in 2D to orthogonal polynomials on a contour without the Hermitian conjugate here. So this becomes non-Hermitian orthogonality. There are lots of things to justify there because your weight function in general is going to be complex. So the norm of Pn is not a norm anymore. So it could become 0, and then the orthogonality goes completely wrong. But, well, you can work around that. This kind of transformation can be done in some cases. It's basically Green's theorem. There's a paper where it was proposed some years ago, exactly for this kind of weights. So Ginevra times one singularity at the point A, and this has been exploited in several other papers. So what is the first idea? The first idea is Ackermann-Vernizzi. They studied this apparently very complicated object. And this is the expectation of very general things. So this is a polynomial, but you allow, okay, polynomial over the eigenvalues, Zj, and then you allow points, you add points xi and points yi bar. Okay, and then they write this thing as, okay, determinant of the correlation kernel. These are van der Mondes, and here you have the norming constants. Okay. This doesn't seem to help too much, but the observation is that if you collapse these extra points, this xi to just 1 point, this yi bar to 1 point, y bar, and then you identify the two, then you have this particular case, and this particular case is nothing but the modified partition function, exactly what you want. The only thing is that this exponent is 2k. It has to be an even integer, and there is nothing you can do about it because this, okay, this k has to be an integer. You are adding an integer number of points here. Size of the determinant has to be an integer. So you get what you want, but not with the full generality in parameters. Still useful. And then the merging is a bit of a mess if you are not careful, because you have to merge. This becomes a 0 over 0. So when you merge, you have to be careful. And essentially, you have to take all sort of partial derivatives of your kernel here. So it takes a bit of rewriting sometimes if you have, because your kernel will depend on these variables x and y. So it's important that you try to get a formula for the kernel that separates these two variables x and y. Otherwise, the partial derivatives will be a mess. I'll show what I mean in a minute. So for example, for Ginevra, then what happens is that, okay, this object, which is what we want to understand, with even integer parameter here, is this expectation, and then you go to the formula of Ackermann-Vernizzi, and you need this kernel. This kernel is the sum of polynomials over this, over hj, and these polynomials, because the weight is rotational invariant, these polynomials are just monomials. And then you have this sum, and then this sum you can identify as an incomplete gamma function and rewrite it in this form. And this is much better. Remember what I said before, you need to take derivatives with respect to x and respect to y. This is much better than this, because here you take successive derivatives, okay, under the integral sign, but essentially they are going to, computation is not too bad. Okay, so then if you compute that, skipping the details, what you obtain is that for integer parameter, this partition function can be written as follows. So this is a prefactor, very explicit, and then you arrive at a certain probability over a Hermitian random matrix ensemble. This is the Laguerre. So it's a cap probability, the probability that k by k Laguerre unitary ensemble, the smallest eigenvalue is bigger than this quantity. That depends on n and depends on where you put your x here, where your singularity is located. Okay, so this is a kind of sometimes called duality formula, because it relates a non-Hermitian object, an object coming from non-Hermitian ensemble, to an object coming from Hermitian ensemble, which is much nicer. Okay, and this LUE appears, is not too difficult to believe because of this construction. You take derivatives, and essentially what you get is some Laguerre type integral. Okay, so the important thing, again, duality, and then k has to be an integer. So basically you swap n by k, which is nice, and it's also nice for asymptotics, because over here n can be taken large, but it's not the size of the matrices anymore. It's much easier. It's a parameter in the integral, and then it's much easier to control. What happens if gamma is not an even integer? Well, there's a result, again, for tracing Widom, that identifies this gap probability for LU for Laguerre in terms of a solution of now Painlevé 5. And this is the sigma version of Painlevé 5. And then you may say, okay, well, here gamma, here I have 2k or k. I can take a real parameter there. Things should be fine. So this identification shouldn't need that k is an integer. So, well, you would expect that the previous duality formula can be somehow extended to non-integer cases. Okay. How can you do that? Well, this is the dirty work of going through Green's theorem. So you start with your planar orthogonal polynomials, and instead of using the duality formula, then you go, well, this is done for you in this case. This is a paper of Webb and Wong a couple of years ago. They show that these polynomials are orthogonal in this 2D sense, but they are also orthogonal in this complex contour way. So you have this orthogonality with this f function that is here, not too bad, where, well, on a closed curve that encircles the interval 0x. You can touch x, but no other points of the interval. Okay, so this is complex orthogonality. Your weight is complex, but okay, you can try to do large n asymptotics and see what happens. It's probably the same thing, yeah. Is it this with one single? Yeah, it should be the same. But in their case, gamma is scaled with n, I think, as well. Yeah, it should be the same. Yeah. And then, yeah, okay, should cite both. Then what happens is that once you do this conversion to contour orthogonality, then you relate this object with prefactor and then a Toeplitz determinant. And this Toeplitz determinant, you can move it to the unit circle, and you have essentially what Toeplitz determinant, and this is your symbol, if you want. Okay. So this is just a change of variables, and then well, moving to contour orthogonality and making a change of variables. And then the result is that you have this identity. Now with general gamma, okay, you need gamma bigger than -2 so that this can be integrated in the complex plane. The density is integrable. And then you have this representation in terms of integral over now the unitary group, or average with respect to CUE. This is on the unit circle. This is a Toeplitz determinant. So this is rewriting again in terms of Hermitian random matrix ensemble, but there you remove the limitation on the parameter. And this object, then you can relate through the work of Forrester and Witte, for example, as a Painlevé 5 tau function. So indeed what should follow from Tracy and Whittam by extending the parameter to non-integers. But of course you have to, well, as far as we understand it, you have to go through this manipulation instead of duality. So another thing that you can do, you can consider, for example, Ginevre ensemble and see what happens when you insert, because all these results, if you want to do asymptotics as n tends to infinity, you have an extra point. The asymptotics will depend on where you introduce this extra point. So if you are in the bulk, inside the unit disk, you get some kind of asymptotics. If you push the extra point towards the boundary, or you put two singularities, 2 points together, then you have a different kind of asymptotics. So for example, this is Webb and Wong. They get the expectation. This is Ginevre with this charge here, this point Z, and they get this kind of asymptotics in the bulk. Z is strictly inside the unit disk. We can consider what happens when Z collides with the boundary, and this is the speed that you have to take with respect to n, the double scaling regime. And then what we get is, well, for integer values of gamma, you get the same prefactor. And here what appears is a gap probability in GUE. So this is a kind of smoothing thing. Becomes 1 inside, so you recover this result. And then it goes all the way to the boundary. Okay, you can check the behavior of this gap probability, which is, by the way, a Painlevé 4 quantity. So it's a kind of the generation from Painlevé 5, which was finite n, to Painlevé 4 as you get asymptotics. Here, gamma is an even integer. Important restriction here. You can study merging of singularities in the bulk. Okay, you push 2 points together with some scaled variables u1 and u2, and then you get asymptotics in terms of, again, LUE, Laguerre unitary ensemble quantities, and it's related to solutions of Painlevé 5. Okay, so very briefly, because I'm going to run over time. In the case of truncated unitary matrices, you can play a similar game. It's more complicated, a bit more complicated. The duality will take you from the truncated CUE, the truncated unitary, to Jacobi. And then you can identify Painlevé 6 tau functions instead of Painlevé 5 for Ginevra. You can consider asymptotics as n tends to infinity, boundary collision, and then this P6 in some way degenerates to P5. And then, okay, the important thing here, for integer k, you can always use this duality to make the identification with the Hermitian random matrix ensembles, and also for asymptotics. But if you look for general values of gamma, then the asymptotic part probably, as far as we understand, relies on Riemann-Hilbert problem for the corresponding Painlevé function. Painlevé 4, if you are in Ginevra. This was studied in a recent paper. But then it's a problem, again, the similar problem that Jonathan mentioned before. How do you, if you deform in a parameter, how do you recover how justify the integration in parameter space and getting the constant term? If you integrate in gamma, the exponent, which is what Webb and Wong do, then the differential equation is a monster. They can still work with it in the bulk, but near the boundary, it looks pretty complicated. You can integrate in x, in the location of the singularity, but now problem, what is the initial value? The initial value could be at the origin. You have Ginevra, great, that's explicit. But if you want to go all the way to the boundary, you you go from one asymptotic regime to another one near to the boundary, so then you need overlap there. And you need asymptotics of the solutions of Painlevé 4 that these people consider. But that's very much work in progress, hopefully not for too long. So I think I'm done. Thank you very much.
Any questions or comments?
Our competition. Thank you.